Okay, hi guys. Dang it, you were just quiet, dog. My dog, Major, is here. I think I've shown you him before. There's his butt. He has a squeaky toy that I hope he stops squeaking so I can record this video for you guys. There it is. Go away. So, sorry I'm not here again, guys. I took some time off to rest my voice, and then I got sick last week. I got a really bad cough, and it completely set me back on any progress I'd made on resting my voice. Currently drinking gobs of hot tea to try and hopefully get it back to normal. But I will be back on Monday. So these first two lessons, thankfully, are very introductory. There's not really many calculations, very, very small calculations, practicing with the basic formula to intro energy, because energy is a doozy. This is our unit here. You can see this on your notes. You should have the notes packet from the sub to fill in. And again, these first two lessons that we're doing today and tomorrow really are a lot of notes filling in blanks. There's not much else, and just kind of working with those concepts in the homework as well. The homework assignments are very small. So you guys really should be able to finish the assignment, this video, and the assignment in each class tomorrow and Friday, and then I will be back on Monday. So let's go ahead and start talking about energy. So we've learned so far about kinematics, how things move. We've learned about forces, and we've learned about circular motion as well. So this unit, again, is starting to talk about the energy of motion, transferring energy between objects, stuff like that. So because of that, so far, we've treated everything as objects with forces acting on them, right? And FBD is all the forces specifically acting on an object, a single thing. However, very often now, we're going to be working with a system, which I've briefly mentioned before. A system is just multiple things inside what we call the system. And we can treat the system as one unit made up of a bunch of objects. An example I will give will be like a pool table with a bunch of cue balls on it. We can instead of treating that as a bunch of separate cue balls, we can think of that as one system. Doesn't make a ton of sense right now. It'll make more sense once we start talking about how energy works. So you always need to define your system, meaning we need to say what's inside our system and what is outside. If it's outside the system, it acts on it. This is really just your choice. If you guys recall how we get to choose the direction of positive. If I want up to be positive or down to be positive, it doesn't matter. The math I do after that has to fall in line with whatever choice I make. So the same thing is here. You could technically do these problems a bunch of different ways and define your system however you want to. But then the math you do has to follow as that choice. There are easier choices. Like again, sometimes it was easier to say up as positive. Sometimes it was easier to say down as positive. Same thing here. Sometimes it'll be easier to choose your system a certain way. So we have two kinds of systems. We have what's called an open system, which is when there is something external acting on the system. It's open because there's something acting outside of it. A closed system means there is no other forces acting on the system. Every possible interaction of forces is included inside what we have chosen to be our system. So let's go ahead and look at the next slide here. So this is an example of, now we're going to talk actually about springs in Unit 6. We used to talk about springs with energy here, and there was an obvious reason why. Springs are really good transfers of energy, but it made more sense for me to put it in Unit 6. So a spring, though, does exert a force on something, right? We've played pinball before, right? You pull the spring back and let it go, and it goes shoop. That's a transfer of energy. Yeah, getting one thing caught back, letting it go, transferring energy. So the marble is attached to a vertical spring, bouncing up and down. So what this means is vertical means it's hanging up and down. So I had a marble on the end of the spring, I let it go, and it goes, yeah. Again, here's like my spring, and there's the marble, and it goes up and down. So ignoring air resistance, because we almost always ignore air resistance, what forces are at play here? Well, the marble can exert forces, right? The marble pulls down on the spring. So the marble, we can say, is one thing in our system. But we also have the spring as well, right? The spring is able to exert a force on the marble because when I drop the marble pulls down, but then the spring is going to bounce back up and pull that marble back up. So the spring is another force at play, but this is vertical up and down, right? I let it go and it goes shoom, shoom, shoom. So what other force is at play here? Gravity, right? It's up and down. Yeah, gravity is affecting that. So we can say gravity as well. So I have choices for how to define my system. All of these things are at play. Any one of these things is just one thing by itself, but I can include whatever I would like in my system. So it says, say we define our system to be just the marble. Are there external forces acting on the marble? Yes, right? And again, just to clarify, what are the external forces acting on the marble? Well, the force of the spring acting on it and gravity. Spring force is actually a thing. We call it spring force. Just like normal force, force tension. It's technically a form of tension, but it works very differently than a rope, obviously. And you guys should understand that a spring is very different than a rope. And then gravity. So if I define my system to be the marble, are there things outside of the marble? Yes. So would we say the system is open or closed? Open, right? Because there are things outside of it. Now say we define our system to be the marble and the spring. Are there external forces acting on the system? Well, if I decide, okay, I'm going to call my marble and my spring the system, is there an external force acting still on this system, the marble and the spring? Yes, gravity is still outside the system. So yes, gravity is still acting outside this system. So is the system open or closed? Still open. Yeah, there's still gravity outside. Now, here is how you include gravity in your system. They say the marble, the spring, and earth. So you will see this in questions. It will say, looking at the marble spring earth system, or looking at the book earth system. Is there anything else? If I choose to say, here's my system, which again, guys, it's going to make more sense when you look at these problems, why I'm saying this is a system. Yeah. Is there anything outside of it? Again, we're not talking about air resistance, so is there anything outside? No. So now that I have included all of the possible forces at play in this situation, this is now a closed system. What we're going to learn is that a lot of times you want to define your system to be closed so that you're including everything that's possibly going on when we talk about energy. Because again, this ball, the marble, is given energy, right? I pull the spring up or down, and I let it go, and then it starts to move. Motion requires energy, which again, we're going to define a bit more in just a bit. So I want to include all of the things that give it energy. So the spring gives it energy and the earth gives it energy. So let's fill in some more blanks here. So let's talk more about what in the world energy even is. So throughout physics, let's talk about this first. There are several conservation laws, which are any laws that states that a physical quantity does not change. That's what conservation means. If you ever see talking about conservation, it doesn't change. Which again, conserved over time, no matter what happens. The very first law is the law of conservation of energy. Now, what this states is that energy can be converted from one type to another, but cannot be destroyed or created. Again, energy is what gives things the capability for motion or heat, right? Heat is a type of energy. I'm kind of getting ahead of myself here talking about that. But energy is really what you think it is. It's just not like a laser beam necessarily, but it's anything that allows something to move. And in fact, motion is a type of energy because that motion has to come from something else. And so that something else gets transferred into the motion. That's the conversion of energy. So energy is the physical measure of the state or motion of an object or a system. State meaning, again, sometimes it's something at rest. It's not actually moving, right? An apple has energy we eat it and we get energy from it, right? So we include all of those things under the same umbrella. So examples, so kinetic energy, again, this is really stuff you should have learned in elementary school or middle school. Kinetic and potential energy are the two big ones. But then also chemical, so like the chemical bonds in the apple are what give us the energy to run, right? We convert the chemical bonds in the apple into kinetic energy, running. And thermal. Thermal is just like heat, right? Fire is an energy, and we can convert a chemical fuel into thermal. I can't create it out of nowhere, yeah? Any type of motion or any type of literal energy you can think of, air energy, heat, water, has to come from something else. This is the idea of conservation of energy, that any type of energy cannot be created out of nowhere. And it also can't be destroyed. It does go somewhere else. Yeah. So that's energy. Let's talk a bit more about the different kinds. So again, we're going to very briefly just talk about the different kinds here. We're not going to talk formulas just yet. So kinetic energy is the energy of motion. Yeah. Running, throwing something, that thing has kinetic energy if it's in motion. Potential energy is the energy that allows for a reversible change to shape or position. So a spring has potential energy because it can go back and eventually comes back to where it stopped, where it started. Yeah, so that's a reversible change. A ball like this, yeah, has a lot of potential energy when it comes up and condenses against the wall. It's building its potential energy and then it springs back and returns to its position. This is also, I'm curious, I'm getting ahead of myself here. I'm going to add a note here, potential energy, a change in height of something is our biggest form of potential energy. If I bring my cup of tea, if I bring it up higher, it has the potential to go faster if I were to drop it and break it. Yeah. If I continue to bring it up higher, I'm giving it more potential to go faster. Yeah. So oftentimes when we think about potential energy, we're thinking about a change in height. The greater the height, the more potential the object has to do something if I let it go. Yeah, it can go faster. We'll learn about that. So with potential energy in particular, you have to be careful about defining your system, because I actually can't say that this cup by itself has any potential, because it doesn't. If I'm just saying my system is the cup, well, all the cup is doing is resting in my hand right now. Inside the system of the cup, it's just the cup by itself. If I define my system, what's giving it the potential, right? What gives it the potential is the earth, right? Gravity. So I would want to define my system to be the cup and the earth to say that it has any potential energy. If I were in space and I just let my cup go, well, there's no gravity. So it has no potential to do anything without the gravity. Again, things we'll talk about more as we continue to work with potential energy. Chemical and thermal energy, we really don't talk about much because chemical energy is very complicated. Breaking bonds between chemicals and converting that into other types of energy, that's chemistry. Yeah, that's actually how, talking about chemical reactions, that's all chemistry. Thermal we talk about occasionally, but just like in, not by a formula. There's no formula for it. Thermal energy is energy that can be dissipated due to heat. So dissipated is not destroyed. It just goes off into space and gets kind of distributed around. Again, like the heat from a candle. Yeah. That energy, that heat does transfer into the air around it, but that energy continues to get distributed around until eventually it's not really doing anything anymore. It's not destroyed, it's dissipated. That's very different. We talk about thermal energy sometimes with energy that's dissipated due to friction, because you know when you rub your hands, they get hot, right? That's actually dissipated energy from you doing this motion. Okay, I got 2 more slides here. Yeah, 2 more slides. So again, like I said, this is just a lot of upfront stuff anyways, so it was a good thing I wasn't here to talk about this in person. So last concept we're going to intro. So as we talked about, energy has to come from somewhere. It's not just created out of nowhere. If I, again, want to raise my arms above my head, that energy comes from inside of me. It's not just magically appearing. If you don't eat, you don't have energy and you die, right? So work then is a physics term that refers to the transfer of energy from one object or system to another through a mechanical process. Yeah, however that process may be. So when a force is exerted on an object or a system, what we do is along its direction of motion, we say that force does work on the object or system. So if I'm outside the system of the cup and the earth, right, and I lift my cup, I am doing work on the system. I am adding energy to the system. Yeah. What I'm actually adding is potential energy, because if I were to drop the cup from here versus here, it has the potential to go faster, right? So again, if I were to say the system is the cup and the earth, and I go whoop, I am doing work on that system. I am adding energy to it. So as we continue to talk about work, the important thing is that, again, it's along this direction of motion. That matters. So if I move something this way, if I move something this way, it's going to matter a little bit what that distance is. So just questions to think about. We're not going to answer these questions, but you should be able to in your head. Is it easier to push a bike or a car? Well, duh, we know that usually it's easier to push a bike. But what if you're pushing the bike up a hill versus the car down a hill? What's easier? Well, the direction is changing. A couple other things are changing. If you had to push the bike 100 miles and the car only 10 feet, what if the distance changed, right? What would be easier? Yeah. So this is the concept of work. I can transfer energy in a bunch of different ways, and it depends on the distance, actually, for one thing, and the direction that I'm applying the force. Okay, so last thing here, and then like I said, all your guys' assignment is getting used to the concept of an open versus a closed system, and practicing with just the other vocabulary, really. So as we expand into our knowledge of energy and work, it's important to understand the law of conservation of energy states that energy in an object or a system must remain constant. This is the whole conserved idea, yeah? Unless there is an outside force doing work on the object or the system. So what this means is that if I define my system to be the cup, yeah, what is outside the cup? If I have it held up here, what forces are acting on this guy outside the cup? Well, my hand, duh, because I'm holding it up, but also gravity, right? Those two things are outside the system. So because right now, currently, my cup by itself has no energy, but I have things outside that will be able to transfer energy into the system, right? If I let go, it is going to drop and gain energy, yeah? Now, however, if I define my system to be the earth and the cup and my hand, there's nothing outside the system. We are actually going to learn that we can calculate the total amount of energy in this system of the cup, the ground, and my hand. Yeah. And when I let go, that total amount of energy is going to stay the same. What happens is it's converted from one type to another. The total amount is still the same, but a conversion happens if it's a closed system. Yeah, if there is something outside the system, the energy will not remain constant because that outside thing transfers energy in. So even if two objects or forces are interacting, if both of those are in the system, we can ignore that interaction because it's not going to change the total energy of the system. This, I will tell you, is going to be helpful to you on one of the questions on your homework. Again, if I were to talk about these two things colliding, my phone and the cup, yeah, think, yeah, they're interacting. That's what we mean, yeah. If I define the system of objects to be both of these guys together, when they collide, I don't think about the total energy of the system changing because they're both inside the system. Yeah. I'm still going to have the same total amount of energy if I define these two guys to both be inside the system. Again, I know this whole idea of a system is probably confusing because we haven't done any calculations. And how you define your system does affect how you do your calculations. So it'll make more sense later, but it'll continue to be very important to define your system and understand what forces are outside. Again, the important thing for right now to know is that the total energy in a system is constant as long as it's a closed system. If you define your system to be open, the total energy will not be constant. Because that, again, those outside things are going to be adding energy. So from here, you're going to go and do the U4L1 assignment. Like I said, should be pretty quick. Shouldn't have any homework. And then tomorrow you'll be doing L2.